first. This is about a this problem is about a sundial, which is basically attached to a wall. Let me sketch it. So this is the wall. I'm going to sketch the wall first. I love this wall questions. And then it is basically towards north and south. So this end go to north, this end go to the south. Let's say this wall has some, it doesn't look like a wall. Now it does. Cool. But let's say this is the wall. Okay, cool. And then you have a stick, which is exactly perpendicular to this wall. So the stick is perpendicular to the wall. So it means it's basically moving. I mean, it's basically looking exactly towards what direction? East, right? East. That's basically the idea. So as sun moves in the sky, it's gonna have a shadow on the wall. So I'm gonna sketch the shadow with purple. This is the shadow, right? So I don't care where the sun is. Wherever the sun is. Okay, I'm not gonna sketch the sun. So as sun moves, this shadow is going to rotate on the wall. So at some point it's here, then it's gonna move here. It's rotating. Rotating. Cool. That's it. So as in the figure, consider a wall oriented north-south. On the eastern side of the wall, there is a rod or gnomon whose axis is perpendicular to the wall, which means it looks towards east. On the sky, take the sun in such a direction that the rod casts a shadow on the wall, like this one. Because the sun moves, this shadow on the wall will rotate. So as sun moves, of course, it's going to rotate. A, show that the maximum angular speed of the shadow's rotation on the wall is going to be omega times cotan declination of the sun, where omega is 360 over 24 hours, and declination is the sun's declination, basically. So this is the first part of the question. Let's see how we can tackle this one. All right. So what I'm going to do first, of course, always, I'm just going to quickly sketch a sphere. This is what we always do. So on this sphere, I do have a Z and P, right? And then directions as well. Here is north, here is south, east, and west. So the thing is, I do know that the gnomon or the stick is looking exactly towards east, right? So this is the direction that gnomon is looking. I also need to find where shadow is looking so that as it moves, so my goal is figure out this angle. I'm going to name it beta, for example. And then beta itself is not important. What is important is d beta over dt, right? So the rate is important, which gives me angular speed, omega. Not angular speed, sorry. Angular speed of the shadow. Omega is something else. Omega is the Earth and angular, sorry, it's the sun's angular speed. And I want this guy to be max, right? That's basically what the question is. Okay. Now I need to figure out where is the shadow going to cast? Shadow is always going to be on this plane. And this plane is the plane which connects north and south and z to one another. In other words, this plane is going to cut the celestial sphere in this great circle. So the great circle that I just sketched is where the highlighted great circle. Highlighted great circle is where the tip of shadow will cast. Right? Cool. But then I also want to show the sun, and I'm only going to be able to sketch the shadow or have the shadow whenever sun is in the eastern hemisphere, right? And this sketch which I made, this is actually showing western region. So I'm going to do another one that shows eastern region, eastern hemisphere, sorry. And then I am also going to add sun's path, something like this. Here is Z, here is P, here is north, here is south, and here is east. All right. So now if here is east, this is my celestial equator. The direction that sun is moving, I'm gonna show it with orange. Let's say this is the sun. Let's say that's sun's path. Okay. Let's assume sun is here at a random point. Do you guys agree that the tip of the shadow, the direction east, and the sun, so the tip of the shadow, I'm going to sketch it with a different color. Let's say with green, something like this, right? So this is where sun is. This tip is exactly the east, and this is the tip of the shadow. All three are on the same line, and it basically gives me a plane. This plane, which consists of the sun, the east, and the shadow, they're all, let me put sun somewhere else, let's say here. These three should be on the same great circle, so something like this. So this point is where the tip of the shadow is going to point at. This point is the tip of the shadow. And as I already mentioned here, the tip of the shadow should be exactly on that circle, on that great circle. NPZS, right? NPZS, great circle. That's basically what I mean. And that is actually there, right? This is exactly there. All right, cool. So far, so good. So now, the angle which I'm actually looking for could be this angle, right? Could be that angle which I'm actually looking at. This angle itself, let's call it beta, is not important, but the change in beta is important, which is basically equal to this one as well. Is it? Yeah. But that one I cannot use. Just trying to think if there's maybe I can use this one. Yeah, this is better. So do you guys agree that the only thing that's going to change here is this angle, right? I'm going to name this beta. As sun moves, this angle is changing. And if that angle changes, it means the shadow is either moving to the left or right here, right? So the beta is the angle which its rate of change. You can find any other angle as well, as long as you can actually measure its change, right? It is the angle which its rate of change gives us the angular what did I call it? Angular speed. Angular speed of the shadow. Cool. So now in this triangle, since this is the sun, here's going to be 90 minus declination of the sun, right? From P to E, this is 90, so this is a very nice triangle. What else I know? What do you guys think this angle is? In terms of sun's. Yeah, it is okay. So since it's P, we measure azimuth from Z, right? So from P, we can either measure alpha or our angle, right? So since sun is here, and this is sun's hour angle, so here is going to be related to sun's hour angle. But again, another question. EPZ. What is this angle? Is that a specific angle you guys know? This angle is exactly 90. It connects east to P and then south, right? This is exactly 90 degrees. That makes sense?
Yeah.
Cool. All right. So if that's 90, it means here this angle is going to be 90 minus T of the sun, right? So 90 minus T of the sun. Cool. Okay, so now that I have that triangle and I'm looking for angular speed of the sun, which is shadow, which is beta dot. So I'm looking for beta dot. Oopsie. Maybe I can, what I can do here. I'm going to sketch that triangle here again because it got a little bit messy. P sun and east, east, P sun. Right. So here is 90 minus T. Here's 90 minus declination of the sun. Here is 90 degrees. And this is the angle I'm looking for, beta. Cool. This is the sun. So now here I'm going to use 4 parts, right? That makes sense. If I use 4 parts, cosine of the inverse, cosine of 90, cosine of 90 minus T, it's equal to sine of 90, cotan of 90 minus declination, minus sine of 90 minus T, cotan of beta. So that being said, this is just 0. This is 1. So at the end of the day, I'm going to have cotan beta. That is cosine t, and then cotan or tan. delta, right? And this is cosine t, right? There you go. So let's say this is equation number 1. Now, if I take derivative of this one, left-hand side is d dt cotan beta d beta dt. Okay, this is what I'm looking for, right? Beta dots, I got it. And right-hand side, I'm gonna have okay, it's t. Anyways, so it's tan declination cosine. It's negative cosine squared t naught sine t, right? dt over dt, right? Yeah. Does this make sense? Now, do you guys agree dt over dt? I mean, this is the change of the hour angle of the sun over time. This is omega. The omega that we talked about up there, right? So this is my equation number 2, which, oh, let me, okay, I didn't. So this is beta, right? dt beta. Cotan beta, we said -1 cosine square of beta, right? No, cosine.
Sine square.
Yeah, sine square beta. There you go. Okay, so this is equation number 2. Now I'm going to mix 1 and 2. To find a relation for beta dot. All right. So beta dot times -1 sine square beta. Sine, cosine. So do you guys agree that I can write this as cosine times, I have a negative 10 times omega, something like this. Is that correct? Yeah. Oh, okay. So 1 over this one, I can write it as 1 plus -1 plus cotan beta, right? Okay, so that makes life easier. So instead of this, I can write -1 plus, and instead of cotan beta, I'm going to write that tan square over cosine square t, right? Something like this. At the end of the day, so then I don't need to write this like that. So I'm going to write this as sine t, and I'm going to write this as negative cosine square t. So what I'm going to do, I'm going to multiply everything by cosine square t. So I'm gonna have also negatives gonna cancel. So beta dot cosine square t and square delta is equal to tan delta sine t times omega. Okay. So we kind of found the relation beta dot equal to delta sine t over. Cool, right? So this is kind of a beta dot how this angle changes, but question is asking for the maximum one. So part B and A are kind of the same thing. How do you guys think we can find maximum? Of course, I can take another derivative and find a maximum, but to be honest, that's going to be pretty long. So instead of that, I can do something and figure out just by looking at it. Can you guess when we can have maximum change? So this is sun's path, right? And it's moving on this circle, small circle. On its path, do you think there's a specific point that, so the thing is, if you look at the shadow is both going to change its length and its direction, both of them. And the only reason that it changes length and direction is sun's motion, and sun's motion in the sky is constant. I mean, the omega that sun's moving, right? So the omega of the sun is basically giving this line or shadow two types of velocities. One, rotational velocity. Second, radial velocity. It's basically being each one gets a share, right? So when rotational is max, I mean rotational velocity is going to rotational, let's say speed is going to be max whenever your radial is minimum. So is there a point that the length of the shadow is not going to change just momentarily? So just look at the path. So when the sun is here, right, and as it moves, does it make sense at this point exactly? Just a little bit before and a little bit after, if you look, the length of the shadow is not going to change. The whole motion here of the sun is going to be spent for the shadow's rotation at that exact point. But at any other point, sun's motion is going to be both being spent on rotation and also change of length. Does that make sense? I mean, if you don't believe me, you can take another derivative of this one, and at the end of the day, you're going to get to the point that t T naught has to be equal to 90 degrees to have beta max. So you can also do that. You can do the algebra method as well. But when T is equal to 90 degrees, which means exactly sun is at this point, you're going to have the maximum rotation. So that being said, beta dot max is going to happen where T naught is 90 degrees. So it means omega 10 declination sine 90 divided by cosine square 90 plus tan square declination, which this guy is 0, this guy is 1. It's going to give us omega 10 over 10, right? And this is 10 squared, so it's going to cancel out. It's going to be omega cotan declination. Right? So that's going to be the maximum beta dot max. And that's basically what question was asking for. It's asking for the maximum. In part B, so okay, to be honest, I kind of wanted you guys to, I mean, to find part A, you might have already figured out part B. But if you were thinking of an, let's say, calculus method of taking derivative and finding that answer, then in part B, I kind of made you to think about this fact as well, that it's only going to happen when T is 90, and that's it. There's a reason for it, right? So I want you guys to understand the reason. Otherwise, I know you can do the calculus, math as well. So this was A and B.